Okay, now let's take a look at the resistive element, or the first element, as our first element to study. So this is an example of this. You have, like, for example, here, dampers, resistor, fluid, pipes, valves. These are the ones that we have. And in here you have the representation of the R element is like this. It has the R element over here, says, and here's the rest of the system. So if the R element presses on the system with this variable E, the red one, the system will respond with F. The point, however, that what's important here is that this equation reflects this picture. See? And this picture reflects this equation. So I think it might be a good idea to do an example at this point. And to do that, let's break from the presentation onto my set of notes in here. And then we'll just go in here and pick up a nice color to begin with. And let's just make a little drawing here of a damper like this. And we have in here, and then we say, okay, these are this is the force here, and this is the force on the other side. So isn't it true that you can easily say that F is equal to this, we use the constant B times x dot, right? That's so we say this is force equals to B times velocity, right? That's how it works. But if we write the equation this way, we say the R element R, the output is F. And so we have this kind. So we say that F is equal to B times the velocity, in this case F, right? So this is we usually use this notation to put it this way. You could say, maybe let's just make a little line in here to divide. You could say, but we can write the equation as, isn't it true, you could say that x dot is equal to 1 over B times F, right? This is correct also. If this is true, and this we are saying velocity is equal to a constant, which in this case 1 over V times force. Or now I am going to begin doing my thing with this bone graft models. Just, but this, isn't it true that saying flow is equal to a constant 1 over B times the effort, right? Just like here, see, this one says effort is equal to the constant B times flow. If this is true, then it follows that the R element that I had in here, let's just do it with a consistent color over here. Just put the R element in here. That this, yeah, it says the flow is the output. So now this has to be like this. I don't know if it's easier to write, to draw a line. You just do a line to see if I maybe it's easier that way. And I could just say R and then go pick another line over here to do it this way. Yeah, it looks nicer. And then we could just erase this one, like that. Yep, it looks much nicer drawing it that way than trying to draw my lines in here. What I am trying to say is, maybe I'll go over here, is that the causality, as we call this thing here, is directly related to the equation. And here, as well as the causality this way, is this equation. So you could begin to see that Painter's thinking was not just on the variables. He says, wait a minute, if we put this little symbol in here, will affect also how the equations are defined. And I think that's what was the best contribution to the field, was to be able to define it so clearly and concisely, all these variables that otherwise become an integral part of systems, and they are not that easy to relate at the begin with. So now that you know the Simulink notation, you also know that this equation can be written this way in block diagram form, or this way in block. Since we are now in this mode of doing these equations, why don't I just maybe do some annotations in here and see what does this mean. This means that F is equal to E times 1 over R. This little equation like this, can be represented this way or this way. Both are totally equivalent. And if you have it over here like E is equal to R times F, this equation that you see in there, in fact, is this representation, or it is this one. And that's the point I'm trying to make, that in this case, this is your notation in Simulink, right? Simulink. And we use block diagrams for this. And this one is the CAMG notation, and this is the so-called bond graph. I am taking the time to go slow on this, because if you master this difference, you will have no problems in doing the simulations using block diagrams or using bond graph models. Guaranteed. You have no difficulties with it. Okay, let's go back now to the C element, which is the other element that we I need to study. This is like the spring, you know. This is characteristics of these springs, capacitors, accumulators is the relationship between the variable E and Q. In other words, spring is like a capacitance element, like a spring. In fact, again, might be a good idea to do an example. So let me go back to my notes in here, and then we'll do a new page over here. And then you say view. I think it's we put the, yeah, there you go. Let's just go and actually put the thing here, and let's just do a spring. So you have in here the spring, yeah, and then we'll apply a force over here. So I should do the arrows this way, but let's just, it's okay. In this case, so let's just write here spring. Alright, in this spring, we say that F is equal to the constant of the spring times the displacement. So I'm just going to write it down. In here you say force is equal to K times displacement. And in painter's notation we say effort is equal to K times, in this case, displacement, which is Q. The displacement is Q. So I should have written effort E is equal to K times Q. This law, we know in your physics class, is known as Hooke's law. See? And if this is true, if I write E is equal to K times Q, what I have done is write this C element, which is the spring. The output is E here, this E, and in here this is the flow. This is the way this equation, right? This equation says K is equal to the integral of F dt, because the position is the integral of the velocity. Yeah? So this picture justifies this equation. Like I said a moment ago, the symbol goes with the equation. And if you want to write this in another way, in the Simulink notation, for example, just pick a different color to do that. You can say in block diagram form. If you do it in that way, you have that in this case E, the variable E is the, see, you come with F, you multiply this by a constant K, and then you do an integration like this dt, and out of this comes E. See? So you have this equation that you see here can be represented by this notation, or can be represented using this notation. And that's what the slides that I showed you in there show, because Let's go back to that. Seeing here, say see, this in here it has this equation, and this one has this equation. So either you have it in the integral form or you have it in the derivative form. The point is that either way, the C element in this way has this equation, the C element has this equations. I think I would recommend when you're at home studying this, redo these equations on a piece of paper so you can understand what the C does. And perhaps use my notes, use this one. I think if you can redo this at home, I think you'll do just fine. So in here we go.
Can you back that one more second?
Sure. Any question? Yeah, go ahead.
No, the drawing you just had.
Oh, the drawing, mine? This one?
Yes.
Okay.
Thank you.
Okay, you just wanted to see it. Yeah. In here you see, go back over here, and now we have that representation of the C element as I did it on the paper. The only difference is that 1 over S in the Simulink notation is integration, right? That's the difference than what I just did. Now we have the other element, and that is the inertia element. The inertia element in this case has a relationship between the flow and the momentum. So we gotta give some examples of this. And again, just as the presentation up front, you may say, of this element, the I element relates to these equations if you have this configuration, or relates to these equations if you have this configuration. So I think it's not a bad idea if we go back to, we'll come back to this in a moment to this, but let's go back to the notes and create another page in here so that yeah, using the notation. All right, let's just look at the mass system here. Let's say that you have a mass like this, and you apply a force F in here. We know that the velocity of this is defined like this. B is, of course, this is x dot, right, like that. And this is the mass. We know for sure, because of our E110 studies, that the mass is equal to that the force is equal to mass times the derivative of momentum, right? Or we also know this as m times x double dot, right? That's the other way we know this equation. How do we know this equation? How is it called? This is called Newton's law of motion. Newton's law, right? So how this actually is represented in this notation? This is the I element that we say, okay? And then in here, the output of I has to be F. This is F. Okay? So in this particular case, you are saying that, you know, this is effort E is equal to the mass I times dF dt. Yeah. Also, you say that if you go back to the notation that we had in here, see, that corresponds to this. Yeah. So if you if you look at on what we're doing here, you say, okay, this is equal to the derivative of momentum dp dt. So you can write that dp dt is equal to I times df dt. This form that you see here is called the derivative form. And if you do it in a block diagram form, it will show the derivative form. But you can also have this like this, where the output is F is equal to, this is the I element with the mass. Like you say that F is equal to 1 over m times the integral of e dt. So this is called the integral form. And do you remember how this is called in the E110 class? This is called the impulse momentum form. Okay, I'll go back to my slide in here and we'll be finishing up in just a moment. One of them, if you put it in the integral form, will have this block diagram. If you put it in the derivative form, it would have a different block diagram. So I think I want to leave you with this idea that in the integral form it's called the impulse momentum form, and in the derivative form it's called Newton's form.